Hello, everybody, and welcome to the Data Center Knowledge Fast Chat, sponsored by Zinc 5, a look into modern power solutions for digital infrastructure. Really fun topic. I am Bill Clayman, EVP of Digital Solutions and contributing editor to Data Center Knowledge. Joining me today is Steve Jennings, Senior VP from Zinc 5. Hi, Steve. It's good to have you here.
Thank you, Bill. It's great to be here with you.
All right. Let's just jump into this conversation because it's just going to be so much fun. I love power solutions. I love battery technologies, and especially over the past few months, we've seen just how much has evolved. We know, you and I know, and everybody listening knows, data centers consume a lot of power. And in particular, look at how much it's actually, some estimates put it at just about the same amount as the airline industry. Now, it's on pre-March, but that's quite a bit of energy. Now, if we take a look at today's levels of persistent connectivity, we see that data centers are more critical than ever before and also growing in numbers. There was a really interesting AFCOM report that we looked at that saw that the number of data centers is actually jumping, and this is from October, believe it or not. We see that the biggest jump, in fact, came from folks building 5 to 90 locations. So the way that we power these hyperscale data centers, these co-locations, these new edge platforms really has come a long way. And that's what we're going to be talking about. Battery advancements, new megawatt class designs, emerging compatibility conversations, and the way we manage and deliver both power and battery solutions for digital infrastructure has fundamentally evolved. And Steve, this is where we got to bring you in. And I've got just a line of fun questions that I really want to ask you that I'm super curious about. So hope you're buckled in. Everybody listening, sit back, relax. Let's just jump right into this. I'm excited about asking you this one. So when it comes to actually power design and looking at the way we architect this stuff, we really see some interesting and often inspirational advancements. And this is especially true for batteries that are powering some of the most critical and some of the largest ecosystems in our industry. But here's the big question. What do you feel, since your boots on the ground, have been some of the biggest battery advancements? And most of all, why do you think they're important?
Well, Bill, thanks. Importantly, there is a trend away from lead acid batteries, which have been the workhorse of the industry, to other alternative battery chemistries that are offering some improved characteristics. Certainly, lithium has been one of those alternatives chosen, and adoption of it is increasing in the industry. As the industry looks to alternatives, nickel zinc batteries are also of high interest due to their performance, safety, reliability, and sustainability factors. The importance of an alternative like nickel zinc is a lower TCO driven by CapEx factors that folks are looking at, such as smaller footprints, lighter weight, safer battery systems. They even contribute on the OpEx side of things. These are long life batteries, 15-year lives that eliminate multiple lead acid battery replacement cycles. They've got low maintenance and zero cost recyclability. That makes for a very strong business case.
I like everything that you said, right? Because you're forcing people to rethink the way they charge up the powers of their data center, right? That's really, really critical. And I think it's important that, beyond anything else, that you don't get complacent, that you do look at these technologies, which really brings us to this next question. From in-rack kW to megawatt class, you're talking about some massive battery capabilities. How are today's batteries supporting literally some of the largest hyperscale data centers?
Bill, we're seeing new battery alternatives like nickel zinc being considered across a variety of power levels and form factors in the data center.
Mm-hmm.
On the megawatt class side, there's solutions available for traditional battery rooms, but we're also seeing a strong trend in turnkey modular backup solutions that are in the 1.2 to 2 megawatt range. These are skid mounted as well as prefab structures. Then you have distributed backup architectures. These are battery backup units, let's say, versus a traditional UPS that are in rack mounted, and they're defined in standards like the Open Compute Platform or OCP.
Mm-hmm.
Across all of these application areas in the data center, we see footprint, safety, operating temperature, and reliability as the key factors in a battery chemistry being applied successfully.
You know what's really critical? I want everybody to think about what Steve said and also apply it to new concepts around edge computing, because I think that battery tech is going to be impacting what we deploy at the edge quite a bit. Hey, you know what? Let's kind of keep going on this. I'm excited to geek out with you a little bit here, Steve. Let's pop the hood a little bit safely on batteries. Okay. Let's talk about batteries and just how far the chemistry has come. Maybe this is a little bit of a mini 101, but I'd love to get a mini science lesson from you on battery chemistry and kind of what's changed.
Bill, there's nobody I'd rather be geeking out with on batteries. So let's start up here. Fundamentally, there are a couple of different battery types: energy batteries and power batteries. Energy batteries discharge at lower rates for longer periods of time. You'll see them in your Tesla if you've got one of those. Power batteries discharge at high rates for shorter periods of time, and those are a better fit for backup systems. The lead acid battery, which by the way is an energy battery, has moved from flooded designs to VRLA, and there's a variety of chemistries, including lead calcium, absorbed glass mat, gel, thin plate pure lead. All of these were aimed at improving performance to compete with the newer alternatives that are in the marketplace today. So let's take a look at what else is there. Lithium. That's come onto the scene, and we're seeing a variety of chemistries, including lithium titanate, or LTO, or a combination of lithium manganese oxide, LMO, and nickel manganese cobalt oxide, NMC, all in one battery style. And there's lithium iron phosphate, which some think is going to be the more popular lithium chemistry as we go forward in the future. And while all of these are lithium chemistries, they have different performance parameters that users should evaluate. Let's take nickel zinc. Nickel zinc is a power battery, which is the type of battery best suited for backup because its high power density enables a small footprint while offering high discharge rates with no risk of thermal runaway. The chemistry also has significant reliability improvements over lead acid and lithium. For example, when a cell fails in a lead acid or lithium string, it could become an open circuit or high impedance that disables the string from charging. With nickel zinc, a weak or depleted battery cell remains conductive. That allows the battery string to discharge and support the load. Batteries in UPS systems have been identified as a significant contributor to data center outages, and this characteristic of nickel zinc changes the reliability of battery strings. So as you can see, there's a variety of battery choices out there, multiple chemistries in each type, and different characteristics. So it's important that users evaluate truly what their needs are and look at the newer chemistries that can offer them advantages they've never had before in battery strings.
I like that. I feel like I just got the periodic table dropped on me, but let's talk about some of those newer chemistries, because we're down to our last minute here. Let's look at the future a little bit. What is your vision specifically around the current battery makeup and technologies, lead acid solutions, let's say, compatibility, and really what the future ahead looks like? And as a second follow-up quick question for you, Steve, how can organizations actually adopt these new battery technologies without necessarily like ripping out what they already have?
Sure, Bill, thanks. So more lead acid batteries are deployed in the industry than any other battery chemistry. Like I said earlier, it's been the workhorse. The majority of the installed base includes lead acid compatible UPS systems. So for users who want to move to an alternative chemistry at, say, the next lead acid replacement cycle you have, it's important for any new chemistry to easily retrofit to that existing installed base. Let's give an example here. Nickel zinc battery cabinets are designed to be a drop-in replacement for lead acid, and this capability dramatically reduces switching costs for users. Other battery chemistries may not be able to drop in like this due to difficult compatibility issues, but drop-in replacement means the UPS manufacturer does not have to go through a design change, so users specifying even new systems can confidently choose an alternative like nickel zinc for new installations.
That's fascinating, and definitely something to continue to explore. I think we're out of time here, though. Listen, everybody, battery technology is a blazing trails out there, and I definitely recommend everyone learn some more. But to reference more about the information that we learned about today, be sure to check out zinc5.com. Thank you again, Steve, for joining us, and thank you again to Zinc5 for sponsoring this Fast Chat.
Thanks very much, Bill. A pleasure to be here.